Welcome to the Explainer. Today we're talking about the fundamental rulebook for the entire universe. I'm talking about the laws of thermodynamics. And trust me, this isn't just some abstract physics class. These are the rules that explain everything, from how your car engine works to how stars burn. So let's just dive right in with a question. A dream, really, that has kept inventors up at night for centuries. Imagine a machine that could power itself, a source of infinite, free energy. Is something like that just really hard to build, or is it flat out impossible?
Yeah, this dream has a name. You've probably heard it, the perpetual motion machine. And for the longest time, it felt like it was just around the corner. But to really understand why it's always just a dream, we have to kind of become detectives and follow the clues hidden in the science of energy.
Now, this specific kind of machine is called a perpetual motion machine of the first kind, or PMM1 for short. And that first kind part is super important. It means this is a machine that supposedly does work forever without taking in any energy at all. Basically, it's a machine that claims to create energy right out of thin air.
Okay, to see why that's a huge red flag, we have to define our playing field. See, in physics, you can't just talk about energy in some vague, hand-wavy way. You've got to be super precise about what you're looking at and, just as importantly, what you're not looking at. So here's what scientists do. They draw an imaginary little bubble around whatever it is they're studying. Could be an engine, a beaker of chemicals, whatever. That's the system. And everything else? Everything else in the entire universe? That's the surroundings. Simple as that. And this is a perfect way to picture it, right? You've got the system, the surroundings, and that all-important boundary between them. Now, energy can cross that boundary for sure, but it has to follow some very strict rules. Think of it like a tightly controlled border crossing for energy. So before we even get to the first law, we have to talk about the zeroth law. I know, it sounds like they forgot one and added it back in later, which is kind of what happened, but it's actually the foundation for all of this. It just says that if object A is the same temperature as B and C is the same temperature as B, then A and C have to be the same temperature. It's so obvious, but it's the reason thermometers actually work. Okay, so our stage is set. We've got our system and our surroundings. Now it's time to meet the two main characters of our story, the two ways that energy actually gets across that boundary. Their names are work and heat. Let's start with work. And listen, we have to be really clear. This isn't the kind of work you do at your job. In thermodynamics, work is an organized, orderly transfer of energy, like a piston pushing or a motor turning. The classic definition is anything that could, in the end, be used to lift a weight. This picture just nails it. The system, the battery and motor is doing work. And how do we know? Because its one and only effect on the outside world, the surroundings, is that it's lifting that weight. It's a direct mechanical energy transfer. That's work.
But what about our other character, heat? Well, heat was a lot more mysterious. For ages, scientists actually thought heat was a real substance, an invisible fluid called caloric that would literally flow from hot things to cold things, kind of like pouring water from one cup to another. It was a neat idea, but it was completely wrong.
The whole game changed thanks to this guy, James Joule, back in the 1840s. He built this brilliant little contraption. You have a falling weight, and we know that's a form of work, right? And it's hooked up to a paddle that churns the water in an insulated box. And all that churning and friction, it heated up the water. Now, Joule was obsessive about this. He would measure exactly how far the weight fell, so he knew precisely how much work was being done. And at the same time, he measured the temperature of the water down to a fraction of a degree. He did this again and again and again. So, what do you think he found? He found a perfect, direct connection. And this was the huge aha moment. Joule proved that the amount of mechanical work he put into the system was directly related to the amount of heat that showed up. Work could become heat. They weren't two different things at all. They were just two different faces of the same thing: energy.
This realization is, and I am not exaggerating, one of the most important truths in all of science. It's the law of conservation of energy. You can't make it, you can't destroy it. All you can ever do is change its clothes, turn it from chemical to electrical or from mechanical to thermal. But the total amount, it always stays the same.
And this beautiful little equation says it all. The change in a system's energy, that's delta E, is simply the heat you add to it minus the work it does. That's it. It's a perfectly balanced budget. There are no secret offshore accounts or weird accounting tricks. The universe's energy budget is absolute. Okay,
So now we're armed with this unbreakable law of the universe. Let's go back to our mystery. Let's go back to that impossible machine and finally crack this case wide open.
So, why is a perpetual motion machine of the first kind impossible? It's actually really simple now. It breaks the first law. To produce work, to lift that weight or turn that wheel forever, it has to get the energy from somewhere. It either has to burn through its own internal energy or take in heat. It cannot just create work. It's like trying to make a withdrawal from a bank account with $0 in it. The universe will just look at you and say, sorry, transaction denied.
And don't for a second think this is just some abstract theory. This law is running our entire world. It dictates how efficient our power plants can be, how your car engine works, how your refrigerator moves heat around, and it even governs the metabolism in your own body. That's turning your last meal into the energy you're using to process this right now.
But wait a minute. The first law says energy is always conserved. It never disappears. So if that's true, then why do we even have energy crises? Why can't we just grab all the waste heat coming off a car and use it to power the car again? If energy is never lost, why does everything seem to eventually run down? That, right there, is probably the deepest question of them all. And the answer is waiting for us in the second law of thermodynamics, the law that explains why time only flows in one direction, and why, even though the amount of energy never changes, its quality does. And that, well, that's a story for another explainer.